Welcome to this coding problem walkthrough. Today, we'll be tackling LeetCode problem number 2188, minimum time to finish the race. In this problem, we aim to minimize the total time required to complete multiple laps in a race, using a combination of strategies. Stick around as we explore the approaches, analyze their complexity, and break the solution down step by step. In this problem, you're participating in a race with multiple laps, and your goal is to finish the race in the minimum time possible. For each lap, you have two options to complete it. First, you can use a new set of tires, which involves taking a fixed amount of time to change the tires, called change_time, and then completing the lap with a specific time, known as initial_lap_time. The second option is to continue using the current set of tires. However, as you reuse the same tires for multiple laps, the time to complete each lap increases due to tire degradation. This degradation is modeled as a multiplication factor f, applied for each successive lap. For example, the first lap with the same tires takes initial_lap_time, the second lap takes initial_lap_time *f, the third lap takes initial_lap_time *f*2, and so on. Your task is to determine the minimum total time needed to complete all the laps, given specific details about the tires, the time to change them, and the total number of laps in the race. Now, let's break down the input and output formats for this problem. The input includes three components. First, there's a list of tires, where each tire is represented as a pair, initial_lap_time, f. Here, initial_lap_time is the time it takes for the first lap using that tire, and f is the degradation factor for subsequent laps. Second, you are given a single integer change_time, which is the fixed time required to change tires. Third, there's number_laps, which specifies the total number of laps in the race. The output is straightforward. You need to return a single integer that represents the minimum time required to finish the race. To clarify this, let's look at some examples. In the first example, the input specifies two types of tires, a change_time of 5 seconds, and a total of 4 laps. By carefully planning how we use the tires, we can complete the race in 21 seconds. Here's one way to achieve this: use the first tire for the first 2 laps. The first lap with this tire takes 2 seconds, and the second lap, due to degradation, takes 2 multiplied by 3, which is 6 seconds. After these 2 laps, we change the tires, which takes an additional 5 seconds. Then, we use the first tire again for the remaining 2 laps, following the same pattern. The first lap takes 2 seconds, and the second lap takes 6 seconds. When we add up these times, 2, 6, 5, 2, and 6, we get a total of 21 seconds, which is the minimum time to finish the race. Let's explore another example. In the second example, we have two types of tires, a change_time of 10 seconds, and a total of 3 laps. The optimal strategy here is to use the second tire for the first 2 laps. The first lap with this tire takes 2 seconds, and the second lap takes 2 multiplied by 2, which equals 4 seconds. After these 2 laps, we change the tires, taking 10 seconds, and then use the second tire again for the final lap, which takes 2 seconds. Summing these times, 2, 4, 10, and 2 gives a total of 14 seconds. This is the minimum time required to finish the race in this scenario. Let's also consider some constraints and edge cases to better understand the problem. There are a few important edge cases to consider in this problem. First, if there's only one tire available and only one lap to complete, the minimum time is simply the initial_lap_time of that tire. Second, if the degradation factor f is very large, it will likely be more efficient to change tires frequently rather than reusing the same set for multiple laps. Third, when the number of laps is very high, you'll need to carefully balance the trade-off between minimizing tire changes and the increasing lap times due to degradation. Finally, if multiple tires are available with different properties, the algorithm must evaluate each option to find the globally optimal solution that minimizes the total time. These considerations ensure that your solution is robust and efficient for all possible inputs. To solve problem number 2188, minimum time to finish the race, we need to minimize the total time required to complete a series of laps. The complexity arises from the trade-off between reusing the same tires, which wear out over time, and switching to new tires, which incurs a fixed cost. The brute force approach is the simplest method to understand. Here, we compute all possible combinations of lap times by exploring every sequence of either using the current tire or switching to a new one. For each lap, we calculate the time required for both options, and recursively consider all combinations across multiple laps. However, this approach is highly inefficient. As the number of laps increases, the number of possibilities grows exponentially, leading to a time complexity of 2 to the power of n in the worst case. This makes the brute force approach impractical for larger inputs, as it quickly becomes computationally expensive despite being straightforward to implement. Therefore, while it provides a foundation for understanding the problem, we need a more efficient solution for real-world scenarios. A much more efficient approach is to use dynamic programming combined with pre-computation. The key insight here is to pre-compute the minimum time required to complete a sequence of laps using a single set of tires, taking into account the exponential growth of tire wear and the cost of switching tires. By doing this, we can avoid redundant calculations during the main computation. The implementation involves two main steps. First, we pre-compute the minimum time for completing up to k laps with a single tire, where k is the maximum number of laps before switching becomes suboptimal. Second, we use dynamic programming to calculate the minimum time for completing all n laps by combining these pre-computed results. This method ensures that we only compute what is necessary, significantly improving efficiency. The pre-computation step has a time complexity of k, and the overall DP solution runs in n*k, where n is the number of laps. Compared to brute force, this approach is scalable and strikes a good balance between efficiency and correctness. However, it does require additional pre-processing and storage. Another option considered was the greedy approach, which selects the shortest time for the next lap at each step. While this method is fast with an n complexity, it often fails to achieve the optimal result, as it doesn't account for long-term decisions, such as preserving a tire for later laps. Thus, the dynamic programming approach is preferred due to its balance of efficiency and accuracy. The chosen strategy to solve this problem is dynamic programming with pre-computation. A key observation is that tire wear grows exponentially, making it inefficient to use the same tire for too many laps. By pre-computing the minimum time for completing k laps with a single tire, we can efficiently construct the solution for n laps using the principles of dynamic programming. The aha moment here was recognizing that the problem can be broken into overlapping subproblems, which makes DP a natural and powerful fit. This strategy was chosen over the alternatives for several reasons. The brute force approach, while simple, is computationally expensive and infeasible for larger inputs. The greedy approach, on the other hand, is faster but fails to guarantee an optimal solution, as it neglects the long-term impact of decisions. In contrast, the dynamic programming approach is both efficient and accurate, leveraging pre-computed values to avoid redundant calculations. The trade-off involves the additional pre-processing step, which requires some extra computation and storage. However, this is a small price to pay given the significant reduction in computational cost during the main DP computation. With an overall complexity of n*k, this approach is well suited to handling the constraints of the problem, ensuring that we achieve the minimum time to finish the race while maintaining computational efficiency. In this problem, we are tasked with minimizing the total time required to finish a race consisting of n laps. The unique aspect of the problem lies in the trade-off between reusing a tire for multiple laps and switching to a new tire, which incurs a fixed pit stop cost. The challenge arises because the time it takes to complete consecutive laps with the same tire increases due to wear, modeled by a multiplicative factor r. For example, with a tire that has f equals 2 and r equals 3, the times for consecutive laps would grow exponentially as 2, 6, 18, and so on. On the other hand, switching to a new tire resets the lap time to its initial value but adds the switching cost change time. To solve this, we need to determine the optimal strategy that minimizes the total time by carefully balancing these two factors. Now, let's break down the algorithm step by step. First, we pre-compute the minimum time for completing laps using a single tire without switching. For each tire, we calculate the cumulative times for consecutive laps until it becomes more efficient to switch tires. This is determined by comparing the time for the next lap with the cost of switching plus the initial lap time of a new tire. These values are stored in an array called best_single_tire, where each entry represents the minimum time to complete a specific number of laps with a single tire. Next, we use dynamic programming to find the optimal total time for completing n laps. We define a DP array DP where DP, I, represents the minimum time to complete I laps. Starting with DP, 0 equals 0 as the base case, we iteratively calculate DP, I, by evaluating all possible strategies. For each lap count I, we consider completing some J laps using the pre-computed single-tire strategy, then switching for the remaining laps. The minimum of these options gives us the value of DP, I. Finally, the result is stored in DP, N, which represents the minimum time to complete all N laps. To better understand the algorithm, let's highlight a few key insights. First, the exponential growth in lap times due to tire wear necessitates periodic switching of tires. This creates a balance between reusing a single tire and incurring the cost of switching, which is central to minimizing the total time. Pre-computing the cumulative lap times for each tire is a crucial optimization, as it allows us to focus only on feasible options during the dynamic programming step. This reduces the overall computational complexity. The dynamic programming approach itself ensures that we systematically explore all combinations of reusing tires versus switching, guaranteeing that we find the optimal strategy. The two main data structures we use are the best_single_tire array, which stores pre-computed times for completing a given number of laps with a single tire, and the DP array, which keeps track of the minimum times needed for completing each number of laps up to n. Analyzing the complexity of this algorithm, we see that the pre-computation step has a time complexity of O(m*k), where m is the number of tires and k is the maximum number of laps a single tire can run before switching becomes optimal. The dynamic programming step has a time complexity of O(n*max_laps, where n is the total number of laps and max_laps is the maximum laps a single tire can run. Combining these, the overall complexity is manageable due to the small values of k and max_laps in practice. Additionally, we need to account for edge cases. For instance, when n equals 1, the algorithm should correctly handle this simple case. If the switching cost is very high, the solution must favor reusing the same tire for as many laps as possible. On the other hand, with higher values, the wear factor causes lap times to grow rapidly, requiring the algorithm to adjust its strategy accordingly. Let's walk through an example to see the algorithm in action. Suppose we have two types of tires, one with F equals 2 and R equals 3, and another with F equals 3 and R equals 2. The pit stop switching cost is change time equals 5, and the race consists of n equals 4 laps. First, we pre-compute the best_single_tire values. For tire 1, the lap times are 2, 6, and 18, with cumulative times of 2, 8, and 26. For tire 2, the lap times are 3, 6, and 12, with cumulative times of 3, 9, and 21. Next, we use dynamic programming to calculate the minimum time for each lap count. For DP1, the minimum time is 2, since tire 1 is the fastest for a single lap. For DP2, we compare reusing a tire versus switching and find the minimum time to be 9. Finally, for DP4, we evaluate all strategies and determine the minimum time. The result, stored in DP4, is the optimal time to complete all 4 laps. This illustrates how the algorithm balances reusing tires and switching effectively to minimize the total time. This solution tackles the problem of minimizing the time to complete a race with number laps using dynamic programming and pre-computation. Here's a detailed explanation of the code. 1. Pre-computing single tire lap times *. We define a maximum number of consecutive laps, max_laps, that can reasonably be completed with a single tire, set to 20 for practical reasons. We calculate the minimum time required to complete k consecutive laps with any single tire from the tires list. This is stored in the min_time_for_k_laps array for quick access later. For each tire, F, R, the initial lap time is F, and subsequent laps take F*r, F*r squared. The loop stops early when changing the tire becomes faster than continuing with the current one. 2. Dynamic programming initialization *. We set up a DP array where DP, I, represents the minimum time to complete I laps. dp0 is initialized to 0 since no time is needed for 0 laps. 3. Filling the dp array asterisk. For each lap count from 1 to number laps, we consider all possible ways to complete the last k laps, where k ranges from 1 to max underscore laps. The time for these k laps is fetched from min underscore time underscore for underscore k underscore laps, k. If k is less than the total laps, we add the change time since a tire change is required. The dp value for the current lap count is updated to the minimum possible time using these options. 4. Final result asterisk. The result for completing number laps is stored in dp, number laps, and returned as the final answer. This approach efficiently combines pre-computation and dynamic programming to minimize redundant calculations, ensuring the solution is optimal and runs within the problem's constraints. Here, we begin the Java implementation for solving the minimum time to finish the race problem. The first step is to define the maximum number of laps a single tire can handle before it becomes more efficient to change the tire. This is represented by the variable maxLaps, which we set to 20. We then create an array minTime for klaps to store the minimum time required to complete klaps with a single tire, initializing all values to integer.max_value as placeholders. Next, we iterate over each tire in the tires array, where each tire is represented by an array containing f, the time to complete the first lap, and r, the multiplier that increases the time for subsequent laps. The goal here is to pre-compute the fastest possible time to complete up to max laps using a single tire. Inside the loop, we calculate the time for each lap and accumulate it into total time. If at any point the time for the next lap exceeds the cost of changing the tire, we break out of the loop, as it is no longer optimal to continue with the same tire. This pre-computation ensures that we have the minimum times readily available for the dynamic programming step that follows. Now, we move on to the dynamic programming portion of the solution. We initialize the dp array, where dp, laps, will store the minimum time to finish laps. The array is filled with integer.max_value to represent uncomputed states, except for dp, 0, which is set to 0 since no laps requires 0 time. For each possible number of laps from 1 to number laps, we calculate the minimum time by considering all possible ways to split the laps. Specifically, for each valid k laps that can be completed with a single tire, we update dp, laps, with the minimum of its current value and the time taken to complete k laps, plus the time already computed for the remaining laps, k. If the current number of laps equals k, we skip adding the tire change time since no further change is needed. This nested loop ensures that we account for all combinations efficiently. Finally, the value of dp, number laps, gives us the minimum time required to complete all laps, which is returned as the result of the function. We begin with the first example, where the tires are given as 2, 3, the change time is 5, and the total number of laps is 4. The first step is to pre-compute the minimum time required to complete k laps without changing the tire. For the tire, 2, 3, the base time f is 2 and the multiplier r is 3. Starting with the first lap, the time is simply f equals 2, so min_time_for_k_laps, 1, becomes 2. For the second lap, the time is calculated as 2 * 3 equals 6, resulting in a total time of 8 after 2 laps. This updates min_time_for_k_laps, 2, to 8. For the third lap, the time increases significantly to 6 * 3 equals 18, and the total time becomes 26. However, since this exceeds the cost of switching the tire, which is f plus change time equals 7, we stop further calculations for additional laps. The result of this step is that min_time_for_k_laps contains the values inf, 2, 8, inf, indicating that only the first 2 laps are feasible with this tire without a change. Now, we use dynamic programming to calculate the minimum time to complete all the laps. The dp array is initialized with dp, 0, equals 0 and all other values set to infinity. For the first lap, we directly use the pre-computed value, so dp, 1, becomes dp, 0, plus min_time_for_k_laps, 1, equals 0 plus 2 equals 2. For the second lap, we try all possible values of k. using one lap at a time, dp2 is updated to dp1 plus min underscore time underscore for underscore k underscore laps 1 plus change time equals 2 plus 5 equals 9. However, by completing 2 laps without a change, the value becomes dp2 equals min 9 dp0 plus min underscore time underscore for underscore k underscore laps 2 equals min 9 0 plus 8 equals 8. For the third lap, we again use one lap at a time, leading to dp3 equals dp2 plus min underscore time underscore for underscore k underscore laps 1 plus change time equals 8 plus 2 plus 5 equals 15. Finally, for the fourth lap, repeating the same process gives dp4 equals dp3 plus min underscore time underscore for underscore k underscore laps 1 plus change time equals 15 plus 2 plus 5 equals 22. The final result is dp4 equals 22, meaning it takes 22 units of time to complete all 4 laps. In the second example, we now have 2 tires, 1, 2, and 2, 2, a change time of 3, and a target of 3 laps. The first step is to pre-compute the minimum time 4k laps for each tire. For the tire 1, 2, the first lap takes 1 unit of time, so min underscore time underscore for underscore k underscore laps 1 equals 1. For the second lap, the time becomes 1 plus 2 equals 3, updating min underscore time underscore for underscore k underscore laps 2 to 3. For the third lap, the time exceeds the cost of switching the tire, so we stop. For the tire 2, 2, the first lap takes 2 units, but this does not improve min underscore time underscore for underscore k underscore laps 1, as we already have 1 as the minimum. For the second lap, the time exceeds the switch cost, so no further updates are made. The result of this step is that min underscore time underscore for underscore k underscore laps contains INF 1, 3, INF, where only the first 2 laps are feasible. Next, we calculate the minimum time using the dynamic programming approach. The DP array is initialized as 0, INF. For one lap, the minimum time is dp1 equals dp0 plus min underscore time underscore for underscore k underscore laps 1 equals 0 plus 1 equals 1. For 2 laps, we consider all possible values of k. Using one lap at a time, the time becomes dp2 equals dp1 plus min underscore time underscore for underscore k underscore laps 1 plus change time equals 1 plus 3 equals 5. Alternatively, completing 2 laps without a change gives dp2 equals min 5 dp0 plus min underscore time underscore for underscore k underscore laps 2 equals min 5 0 plus 3 equals 3. For 3 laps, again using one lap at a time, we calculate dp3 equals dp2 plus min underscore time underscore for underscore k underscore laps 1 plus change time equals 3 plus 1 plus 3 equals 7. The final result is dp3 equals 7, meaning it takes 7 units of time to complete all 3 laps. In the third example, we have only one tire, 1, 10, with a change time of 2 and a target of 2 laps. First, we pre-compute the minimum time 4k laps. For the first lap, the time is 1, so min underscore time underscore for underscore k underscore laps 1 equals 1. For the second lap, the time exceeds the cost of switching the tire, so we stop here. The result is that min underscore time underscore for underscore k underscore laps contains INF 1, INF. Next, we calculate the minimum time using dynamic programming. The DP array is initialized as 0, INF. For one lap, the time is dp1 equals dp0 plus min underscore time underscore for underscore k underscore laps 1 equals 0 plus 1 equals 1. For 2 laps, using one lap at a time, the time becomes dp2 equals dp1 plus min underscore time underscore for underscore k underscore laps 1 plus change time equals 1 plus 2 equals 4. The final result is dp2 equals 4, meaning it takes 4 units of time to complete 2 laps. To analyze the time complexity of this solution, we can break it into 2 main parts, pre-computing the minimum time for completing k laps with a single tire, and using dynamic programming to compute the minimum time for completing the total number of laps, laps. First, let's focus on the pre-computation step. Here, we iterate over n tires, and for each tire, we calculate the time required to complete up to max underscore laps. Since max_laps is fixed at 20, the number of iterations per tire is constant. The time for each lap is calculated using a geometric progression, where the cost grows as f asterisk or caret, k1. However, we stop the computation early if the time to continue exceeds the cost of changing the tire. As a result, this entire step has a time complexity of O n asterisk max_laps, which simplifies to O n, because max_laps is constant. Next, we have the dynamic programming step, where we fill a DP array for each lap count from 1 to number laps. For each lap count, we evaluate all possible ways to complete the final segment by considering k laps, where k ranges from 1 to the smaller of max_laps or the current number of laps. This setup allows us to compute the minimum time efficiently for each configuration. In the dynamic programming step, the inner loop for evaluating k laps runs up to max_laps times for every iteration of the outer loop, which iterates over number laps. Therefore, the time complexity for this dynamic programming part is O number laps asterisk max_laps, and since max_laps is constant, this simplifies to O number laps. When we combine the two parts of the algorithm, the pre-computation and the dynamic programming, the total time complexity becomes O n plus O number laps, which simplifies further to O n plus number laps. Now, let's examine the space complexity. During the pre-computation phase, we use an array called min_time_for_k_laps to store the pre-computed times for up to max_laps. The size of this array is max_laps plus 1, which is fixed at 21. Since this size does not grow with the input, the memory usage for this array is constant, or O1. In the dynamic programming step, we use a DP array to store the minimum time for completing 0 to number laps. The size of this array is proportional to number laps, so the memory usage here is O number laps. Adding together the contributions from both the pre-computed array and the dynamic programming array, the overall space complexity of the optimized solution is O1 plus O number laps, which simplifies to O number laps. To put this into perspective, let's briefly compare this optimized approach with a naive or brute force approach. In a naive solution, we might attempt to try all possible combinations of tire changes and lap completions. This would result in an exponential time complexity of O n caret number laps, as the number of combinations grows rapidly with number laps. By contrast, the optimized approach we've implemented leverages pre-computation and dynamic programming to reduce the time complexity to O n plus number laps, and the space complexity to O number laps. This makes the solution not only feasible for large inputs but also highly efficient in practice. The key to this efficiency is avoiding redundant calculations by pre-computing the minimum time for single-tire lap sequences and solving overlapping subproblems only once using the DP array. What makes this approach particularly efficient is the use of pre-computation and dynamic programming to minimize redundant calculations. By pre-computing the minimum time for up to max_laps with a single tire, we eliminate repetitive work in the DP phase. The DP array itself ensures that overlapping subproblems are solved only once, and the constant max_laps bounds the inner loops, preventing any combinatorial explosion. Now, let's break down the best, average, and worst-case scenarios. In all cases, the time complexity remains O n plus number laps, because both the pre-computation and DP steps involve fixed or bounded iterations. The same applies to the average case, as the algorithm's structure ensures consistent performance regardless of input values. In the worst case, the complexity remains O n plus number laps, as well, since the loops are strictly limited by n number laps, and the fixed constant max_laps. Finally, from a mathematical perspective, the geometric progression in the pre-computation phase guarantees a fixed number of iterations, leading to O n, while the nested loops in the DP phase are bounded by number laps and max_laps, resulting in O number laps. Adding these together confirms the overall time complexity is O n plus number laps. One common mistake when solving this problem is neglecting the compounding effect of tire degradation. As tires are reused, their performance decreases exponentially, and if we fail to account for this iterative degradation correctly, it can lead to suboptimal lap time combinations. Another frequent issue arises in the definition of the dynamic programming state. If the state representation is too narrow, such as only tracking the number of laps completed without considering whether a new set of tires is used, the solution may miss key transitions in the optimal path. Additionally, brute force approaches that simulate every possible lap combination without any pruning can lead to exponential time complexity, which is infeasible for large constraints like n up to 10,000. Lastly, overlooking the importance of pre-computing the optimal number of laps each tire can handle before it becomes inefficient to use can result in slower solutions and more debugging challenges down the line. Another pitfall to watch out for is misinterpreting problem constraints. For instance, when n equals 1 or the degradation multiplier b is particularly high, some approaches make incorrect assumptions about the best strategy, leading to suboptimal results. From an interview perspective, this problem is a great example of optimization under constraints, blending dynamic programming with elements of greediness. Understanding how to pre-compute and manage states efficiently is a key insight that interviewers often look for. It's also important to explain why dynamic programming is superior to brute force, particularly in terms of time and space complexity trade-offs. During your explanation, always highlight edge cases, like when only one lap is required or when tire degradation makes long sequences of reused tires impractical. Finally, emphasizing optimization techniques such as pre-computing tire usage and pruning unnecessary states demonstrates a deep understanding of the problem and its constraints. This problem shares similarities with other optimization challenges, making related problems excellent practice. For example, LeetCode 871, minimum number of refueling stops, involves resource management over intervals, similar to handling tire degradation. LeetCode 322, coin change, is another dynamic programming problem where the goal is minimizing steps to reach a target. LeetCode 983, minimum cost for tickets, also combines interval costs and strategy. Lastly, LeetCode 1406, Stone Game 3, incorporates strategy-based dynamic programming to find optimal outcomes. When considering alternative approaches, a greedy algorithm might seem appealing as it always selects the tire with the lowest immediate lap time. However, this method often fails to consider long-term degradation effects, leading to suboptimal solutions in the long run. Another alternative approach is to perform a full simulation of all possible lap combinations and calculate the total time for each. While this guarantees correctness, it is computationally expensive, with a time complexity of 2 to the power of n, making it impractical for larger values of n. The optimal approach involves dynamic programming combined with pre-computation. By pre-computing the maximum laps each tire can optimally handle and using dynamic programming to track the minimal time for n laps, we achieve a significant reduction in runtime complexity to n. While this method requires additional memory for pre-computation, the trade-off is well worth it, as it ensures the solution is both efficient and scalable. Great job! We've now walked through the solution to minimum time to finish the race. By applying dynamic programming and strategic thinking, we tackled this challenging optimization problem. Remember to practice similar problems to strengthen your skills. Thank you for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!